Um, Hi, and thank you very much to Karen and actually all the people who are asking questions there. Um, so I'm going to talk about a similar topic, but I'm going to talk about it much more from a geophysical perspective. I'm going to present some of the results from the recent RIFT project. This is a large multidisciplinary project that involved many universities, but I'm really going to focus on the geodesy work, which has been done in collaboration with Elias Louis, who leads the geodesy group at Addis Ababa University, and also my colleagues at Bristol, Joe Gottsman, Tesfaye Temteme, and Fabian Albino, who are actually the first authors on the three papers that I'm going to present here today. Okay, so there are many reasons for studying continental rifts, and Karen quite rightly highlighted the large population exposure and the potential hazards, but also the resources, and for geophysicists, that's particularly geothermal resources associated with rifts. But actually, I'd like to talk about something a little bit different. And one of the reasons we want to understand continental rifts is because we're trying to understand plate tectonics. We want to understand what leads to continental breakup, what makes the difference between a failed rift, a basin, and a new mid-ocean ridge. And there are lots of numerical models. I've rather oversimplified and sort of just shown you one here, but that's for in the interest of time. But all these models show that magmatic intrusions are really a critical part of continental breakup. And that's because in order to achieve extension through diking, you actually need a much lower yield stress than through faulting. So if you want to rupture the entire lithosphere, the only feasible way of doing that is through magmatic rifting. However, the details of these models do tend to be oversimplified. They're typically based on two-dimensional cross sections, and this is kind of the point that Kathy was, I think, asking about just a minute ago. It assumes that the magma is uniformly distributed along the rift axis. They typically consider basaltic dike intrusions, and they use constraints that are mostly from Afar, but also sometimes from places like Iceland. And my argument here, the kind of root of my argument, is that if we want to understand the processes occurring prior to continental breakup, somewhere like Afar is not the best place to look, because Afar had essentially already reached the point of breakup. The crust and lithosphere are already extremely thinned, and the processes that typify C4 spreading have already begun. So to me, this is a continent. This is part of the continent that's essentially already broken up. And if we want to look at the processes that lead to continental breakup, we need to look at somewhere which still has fairly typical continental crust, 30 to 40 kilometers thick, and full of the kind of inherited structures that are ubiquitous across most continental crust. And we want to establish really whether the patterns of magmatism, the temporal and spatial distribution of magmatism, is the same as in Afar. And I think I'm going to argue here today that it's actually very different. So the technique that I'm going to focus on is Insar. For those of you not aware, Insar is a satellite-based technique that allows us to make these high-resolution maps of surface displacement. And the results you can see on the right here are from a recent survey done with the Sentinel-1 satellite. This is the first 5 years of data from this mission. And really the explosion in availability of data enables us to do continental scale monitoring of both magmatic and tectonic processes. So in conducting this survey, which extends from Afar through all of the eastern branch of the rift down to Tanzania, Fabian identified 18 different deformation signals at 14 volcanoes. So 6 of these are in Afar, 6 of them are in the main Ethiopian rift, and a further 2 in the Kenyan part of the rift. So there's clearly a lot of active deformation of the magmatic systems in this section of the rift. And actually, we've known that magmatism is really important in continental rifting for at least the last 10 years. So back in 2007, there was actually a dike intrusion that was detected by Insar in the Natron Basin of Tanzania. This was associated with quite a large earthquake, a magnitude 5.9 earthquake, and caused a change in eruption style at nearby Oldonyo Lengai volcano, which is obviously famous for being the only active carbonatite volcano in the world. So this triggered a large project, the US Crafty project, who provided a lot of multidisciplinary constraints. And it's just one of the examples of the type of work they've done, shown on the right of this figure here. But their works really highlighted that even in this very early stage of rifting, early stage of magmatic rifting, I should say, magmatism is really important, but so is the transfer of fluids and volatiles through the crust. But what I'm going to focus on today is really what might be considered more typical to the pre-breakup part of the rifting cycle. It's the main Ethiopian rift, and this is usually considered the classic example of a mature continental rift. The extension rate is at 6 or 7 millimeters per year, and there's focused partial melt in the upper mantle that's been extremely well imaged. But importantly for the arguments here today, this is much more like typical continental crust. It's 30 to 40 kilometers thick, and it's full of inherited structures from a long tectonic history. If we look at the surface, peralkaline rhyolites comprise between 40 and 90% of erupted products. This is an old estimate, and as Karen said, I think it's not particularly well constrained. That's between half and most of the erupted products. But it's clear that rhyolites are important at the surface here. We also know there are numerous deforming caldera systems, but until recently there hadn't been any dike intrusions that have been directly detected. There have been some inferred, but none of them had been directly observed or described in any detail. So I'm going to focus in on just 2 examples from the main Ethiopian rift. There are many more, but I'm going to talk about a dike intrusion that happened just to the north of Fintali back in 2015, and it's published in this paper by Tesfaye, and also some long-term uplift that's been happening at Corbetti for at least a decade now. So starting with Fintali, like most of the calderas in this part of the rift, the caldera formed somewhere between 170 and 180,000 years ago. And post-caldera volcanism has been dominated by peralkaline rhyolites. In this case, it's mostly lava flows from aligned vents and fissures, both within the caldera and along the flanks of the volcanoes. It's notable that it's one of the few places with historically described eruptions. In Ethiopia, there was an eruption in 1810 on the south flank of the volcano, which was very close to the town of Metahara. But there's also been lots of documentation of seismic swarms in the area going back to the 1980s. But most recently in 2015, and this one was actually detected by the National Seismic Network. And you can see the earthquakes shown in red here on this map in the area around Tinish Fintali, just to the northeast of the volcano itself. So during his PhD, Tesfaye did a great job of compiling all the Insar data available for this episode. So that's the sentinel interferograms that comprise our survey, but also both ascending and descending tracks. And he also got hold of some data from Cosmos Skynet, which is a satellite that's able to provide much higher temporal and spatial resolution than we get with sentinel data. So what he found was that he could detect deformation to the northeast of Fintali. But if you look at these images, it's quite difficult to pick out in some of them. It's much clearer in the long duration images than the short duration images. And that tells us this isn't a typical dike intrusion that happened within a day. This is probably some protracted period of diking. And he also noticed there's quite a few cracks at the surface that I probably won't have time to go into today, but that's another interesting story. So Tesfaye was able to model this episode with a fairly standard dike intrusion model, a length of 6 kilometers and about 2 meters of opening, which is pretty typical for a dike intrusion of this size. What was unusual was a depth of 6 to 8 kilometers. Most of the dikes we've observed previously have come within 1 kilometer or 2 of the surface. And it's also interesting that it was actually much better aligned with the border faults, which are now inactive, rather than the current extension direction, which is kind of displayed by the 1G fault belt, the active faulting along the 1G fault belt. So once again, this suggests that inherited structures play an important role in this part of the rift. But what's particularly notable about it is the intrusion timescale. So by getting our 4 different data sets and fitting an exponential decay curve, Tesfaye found a typical decay time of something like 83 days. That's nearly 3 months. And to put that in context, all these little dike intrusions that we've seen in Afar that are similar in scale, they've reached their total displacement in less than a day. So this is an order of magnitude longer, 2 orders of magnitude longer. And we were interested in what could cause that. So we turned to a simple source sink model proposed by Eleonora Rivalta, and just shows that the timescale of the intrusion depends on a whole bunch of parameters related to the geometry, particularly of the conduit, and that's very poorly constrained, but also on the viscosity of the melt. And as Karen's already pointed out, the viscosities in this part of the rift are very unusual, very different. We know that in Afar, those dike intrusions were basaltic because several of them reached the surface and erupted, and we were able to sample them. And we can explain this longer time period at Fintali if we take the melt to be peralkaline rhyolite. And so that suggests that this is not a basaltic intrusion like the type, dike intrusion like the type we've seen in Afar and Iceland. It's actually a rhyolitic intrusion that's being fed laterally from one of the evolved magma systems beneath Fintali caldera.
10 minutes.
Okay, so I've got 5 minutes to tell you about the next example, which is Corbetti caldera. And the group at Oxford has done some fantastic work here, giving us some constraints on the eruptive history, and that includes a lot of Karen's work herself. We actually have a long history of volcanism. We know the date for the most recent pumice eruption is about 2,500 years, and since then there's been at least 4 obsidian flows, which gives you a return period of something like 500 years. But importantly for what I'm going to talk about today, we know there's been a high eruptive flux for at least the last 20,000 years through the system. So from a geodetic perspective, Corbetti is unusual because it's been uplifting at a really steady rate since 2009 now. So this is some work from a former student who looked at a range of different satellites and really found that the source was incredibly stable and constant in both in terms of location and rate. And the rate is something like 6.5 centimeters a year, 6 to 7 centimeters a year, which gives us over 70 centimeters of uplift and ongoing by today. So the question has always been what's actually causing this uplift? And at caldera systems, there's a long-standing debate between magmatic and hydrothermal mechanisms. And this is focused on a small number of very well-studied systems, most notably Long Valley caldera in California and Campi Flegrei in Italy. But nobody's really looked beyond that. Nobody's really thought about this in the context of continental rift systems. One thing we have learned from these previous studies, though, is that we're not going to solve this just by looking at deformation patterns. We need to have some other inputs into this. And so back in 2014, Joe Gottsman and I started collecting gravity data from Corbetti. At this point, the uplift signal had only been going on for about 5 years, but fortunately for us, it's still going today. So this is a small number of benchmarks, but they're surveyed incredibly accurately. So we get very high precision measurements. And what you can see just from the first 2 years of measurements here is that we have positive residual gravity changes, which tell us that the material intruding has to be higher density than the surrounding rock. And also that the spatial pattern is very similar to our spatial deformation pattern. So in a simple elastic half-space kind of world, we can look at the deformation to give us a volume change. We can look at the gravity to give us a mass change. And we can combine those two estimates to give us a density. And we have some kind of idea of the possible densities of the fluids that might be responsible for this uplift. So if we do that for Corbetti, we find these numbers. The densities are in excess of 4,000 kilograms per meter cubed. And that's just off the scale. That's physically unrealistic. And similarly, if we look at the pressures associated with these models, we would expect pressures in excess of 100 megapascals, which is much greater than the strength of the rock, and everything would just be pulverized. So these simple elastic models are not realistic. And actually that sort of makes sense because the elastic models work very well for cold continental crust, but we're right above this, right in this caldera system, which we know has a long history of high eruptive fluxes. And in particular, those eruptive fluxes are peralkaline rhyolites. And as Karen mentioned, they're extremely highly fractionated with fractionation depths really in the top 10 kilometers of the crust. So we know there's going to be a lot of residual left behind, and using estimates from petrologists, people like Will Hutchinson, they've estimated that there's got to be an intrusive complex on the order of several hundred cubic kilometers beneath these caldera systems, in the top 10 kilometers beneath these caldera systems. So we can't reproduce these with elastic models, but Joe built a finite element model using COMSOL 5. And within that, we can use some realistic crustal properties from seismic velocity work at Southampton. We can include this intrusive complex. We can also include some constraints on the hydrothermal system from the geothermal companies. And using this model, we can actually match our gravity and GPS, gravity, GPS, and Insar observations with a much more physically realistic set of parameters. So after 9 years, We have excess pressures that are still less than 20 megapascals. That's quite big, but feasible. Our density is somewhere in the order of 2,500 to 2,900 kilograms per meter cubed, and that's consistent with estimates for alkali basalts. It could also be consistent with peralkaline rhyolites, but they would have to be extremely crystal rich for alkaline rhyolites. They probably wouldn't be very mobile if they were that crystal rich. So we prefer the idea that these are actually alkali basalts, fresh alkali basalts intruding into a large evolved mush system. So the volume changes we get using this model are actually significantly larger than from our elastic models. And that's because a lot of the deformation is actually caused by the ductile deformation. And we can also estimate compressibility, which suggests that we actually have some gas in this reservoir, which once again is consistent with the models that Karen was showing us earlier from petrology. So I'd like to kind of bring this all together by talking briefly about the magma budget and continental rifts. We've already had a little bit of a discussion about that, but I think it's a really interesting question. This isn't the final answer, but this is my attempt to put together what we know so far. So at Corbetti, in the last 10 years, we've had about 0.2 of a cubic kilometer of magma intruded. And that's an order of magnitude larger than the dike intrusion that we saw at Fintali. It's also larger, I should mention, than any of these other dike intrusions we've seen in typical continental crust, but it's still significantly smaller than the basaltic dike intrusions, the megadikes that we see in places like Afar and Iceland. So to me, this suggests that in these parts of the rift, continental rifts, true continental rifts, dike intrusions are actually less volumetrically important than the magma fluxes through these caldera systems. And it's worth mentioning that Corbetti is just one of many deforming systems. It's the one we've investigated from this perspective in most detail. But here's just two more examples from Fabian's most recent survey, which shows uplift at both Tulamoy and Suswa, but with very different temporal characteristics. So we're still trying to understand the mechanism for this. But you can also see on the right here that geophysical models are showing large amounts of magma stored beneath these caldera systems. And one of the critical questions comes back to what Kathy was already asking, is this magma just beneath the caldera systems, or does it extend between them as well? So I'm going to leave you there and see if there are any questions.
Thanks a lot. But there's time for one quick question. If you're quick enough, just type it in. All right, Kathy Bader.
Sorry, it's me again. I forgot to look, Juliet. What's happening at Basset? Is there any evidence for deformation there?
No, not yet.
No, interesting. Okay, because it seems to be underlain by a good.
Yeah, so on a geological perspective, our geodetic timescale of 20 years is really nothing. So I think it would be surprising if all of these caldera systems were deforming at the same time. But the fact that we see such a high proportion of them deforming is really quite noticeable.
Thanks.